In our previous video, we were looking at different types of neural networks. We talked about convolution neural networks, graph neural networks, recurrent neural networks, and generally adversarial networks. In this video, we're going to look at the components that make up a neural network now that we know the different kinds. So when we look at our neural network, we need to recognize that there is bias in a neural network. So the human brain, when it assesses information, and of course, a artificial neural network is trying to act like a brain and simulate how we learn. The human brain, it assesses information by how much it agrees or disagrees with existing knowledge and emotions. So when we build a neural network, there is in it bias by how much it's going to agree or disagree when it gets new information, how much of that is it going to relate to. So in terms of the neural network, this is going to be in the form of whether or not neurons fire, whether the information is passed on. So are we going to accept that information or not? And we can fine tune that bias in our neural network. So the amount of bias is going to be how easy it is for information to pass through the neural network. Just like with our brain, when we look at our human bias, that's going to impact how much of that information we're going to retain, keep with us, and use. So we have to recognize that there is that you don't actually keep all information that you're given, right? Some of it we keep and some of it we don't. One, we can see an example of bias in Amazon's application screening process. So Amazon fed a bunch of resumes of successful employees already at Amazon into their algorithm to help identify potential candidates and to automate the screening process. Now, in this case, the input data was based on successful employees already at Amazon, and most tech companies are about 80% male, which means all the data that it was being fed was about men. So the algorithm determined that any resume submitted that mentioned a women's college, a female athletic program, or other indications of feminine gender would not be successful at the organization. So it's an example of bias here because we feed it in a resume. It doesn't match what all the training data says, which is everything that's more male focused. And so we're not accepting that information. And so all of those candidates were rejected from the process. So we have to recognize that bias is going to determine how much we're going to accept of new information and new facts. All right. The other thing we look at in terms of hyperparameters is weight. If we think about how the human brain works, humans put more weight on certain types of information, which is why we talked in some videos about why storytelling is needed. We put more weight on information that contains context that has a story. Well, when it comes to neural networks, the algorithms must also determine how much weight to place on hidden layers and on variables. So deciding how much influence these have on the input. So we can tune the weights in our algorithm. And that's what we're talking about. We're talking about, here's a picture with tree shapes in it. And so how much of that hidden layer, right? Because we never specify in the model that pictures of dogs have trees, but the input all contained pictures of dogs with trees, then the hidden layers start to look for trees. And there's now putting weight on the presence of trees. And so when we ask it to identify a dog, if it doesn't have a tree, it's not a dog. So weights are going to be how much weight we're going to place on those hidden layers and on those variables. We can also see this WhatsApp image generator when you ask it to create a picture of a Palestinian child versus a picture of an Israeli child. The Israeli child has a soccer ball. The Palestinian child has a weapon. Again, it is identifying from if it's fed pictures, and here we're scraping websites, and if it is learning from pictures that portray, Israeli kids playing and being children, but Palestinian kids being more militant, then it starts looking for those militant components, or those become hidden layers within the system. And so then when it's either creating an image or identifying an image, it's now looking for those. So we have to tune the weights to determine how much influence some of those hidden layers can have and how much weight the variables can have. When we're designing a neural network, we have choices to make. We have to decide the type of network. Is it a convolution neural network, a recurrent network? What are we going to do there? We have to decide on the type of training that we're going to do, the size of the data set, the breakdown between the proportion of training and testing data, the number of inputs, so how many variables, what variables are going to be included in this model, and then what are you trying to output? Are we trying to do classification? Do we have multiple classifications, or is it binary? Or are we trying to predict a interval or ratio data point? We have to set the number of hidden layers. So how many layers are we going to have? Even the most simplistic models tend to have about 3 layers, and you can have a lot more. And then how many times are we going to go through the entire model? So we talk about back propagation. We go all the way through and then loop around again. When you're looping around again, that's called an epoch. And so how many repetitions through the training data are we going to do? We're also going to have to choose an activation function, which determines whether a neuron fires. So how much information is going to move to the next part of the neural network. And then as we tune our neural network, we're going to adjust the bias. How easy is it for those neurons to fire? And the weight, how much impact will those hidden layers have on the next layer or the output? When it comes to, I don't know why it jumps all over the place, drives me bananas. When it comes to those activation functions, there are different types of activation functions. So you got to choose which activation function is appropriate for the type of analysis you want to do. So a binary step function is where there's a minimum threshold to send the information through. Otherwise, there is no information passed on at all. In a linear activation function, it's also called a no activation function because all information is passed through. So if all of your hidden layers have a linear activation function, you don't actually have a neural network, you just have a regression model because all the information continues through the entire system. We can have nonlinear activation functions. And so the nonlinear activation functions are sigmoidal, tan, and rectified linear unit and softmax. So a sigmoidal function, A sigmoidal function is used for outputs where you want a probability some event is going to occur. So you use these sigmoidal functions to out that final layer of output when you have a binary classification model. Okay. If you have a regression type model, right before your final output, you will have more of a linear activation function. In terms of if you're doing a CNN for sentiment, then you're going to use a tan function. So a tan function is for where you have strongly negative, neutral, strongly positive. And so then we are going to use the tan function to output for those. So we'll look at that when we do our sentiment analysis with CNN. And then we have the rectified linear unit, which you'll use a lot for a lot of the hidden layers in the middle, regardless of which model you're using, because it's a bit of a hybrid between some binary and linear functions. And there are different versions of it that deal differently with negative values. But really, when you're using that convolution neural network, your hidden layers are mostly going to be this rectified linear unit. And then you'll use one of these other ones for your output, your last step, depending on what you are outputting. If you are doing multi-label classification, so you have multiple categories, then your last layer before your output is going to be a softmax. And that's where a single label is assigned. So they have different graph visualizations here, but really it's good to just kind of capture this, which is softmax is the last one for multi-label, and sigmoidal is the last one for binary. Tan is the last one for sentiment. Okay, and then you're going to use this ReLU a lot for those middle layers. But you might also have binary. If they're all linear, again, then you just have a regression and you're not actually doing a neural network. All right, so the simplest version of a neural network is a multi-layer perceptron, MLP. It can be a classification model or regression model. So you're doing the linear regression or logistic regression to predict some kind of class. You're just adding the hidden layers to it. So it's like the regression we did in the previous videos, but we're adding some layers in the middle. So we have a vector input. So a single variable here that is going to be, you have a number of variables like our multivariable regression. Here we have fully connected neurons. And then we have a nonlinear activation function. So again, ReLU in the middle, and then we'll have, for our classification model, we'll have, like for a binary, we'll do sigmoidal, for example. And then you'll have at least 3 layers. And then in these layers, what you can do is you can specify the number of neurons in the layer, so we can drop some of the information. We can, that's a dropout, set percentage of activations to 0. So we can reduce overfitting, similar to our lasso regression, by dropping some of the information. We can have dense layers. It's going to implement an operation. So we're going to specify the number of neurons in the layer, and we're going to have some activation function using this piece here. And then we can also combine multiple layers. So your layers for these simple models are going to be some function of these, and you'll only have a couple of them. What you will do then is specify how you're going to optimize the model. There are 3 general versions of optimization. And then you have to specify how you're going to measure loss. So we're talking about measurement error. If we have binary classification, we're using binary cross entropy. If we have multiple labels, we are using categorical cross entropy. And if you have more interval ratio type output, then we're using MSE. And we can use similar forms for our metrics like accuracy, or we could use R² or MSE in our model. So we'll take a look at that multi-layer perceptron in our next video.